Welcome back, students. In the previous video, we talked about the mirror formula. We said 1 by f is equal to 1 by v plus 1 by u. F being the focal length and v being the image distance and u being the object distance from the pole. And I told you that you should always use this formula with the sign convention. If you don't use this formula with the sign convention, this formula will work for certain cases and will not work for certain other cases. This formula without the sign convention will still work for cases where you have real images, but it will fail when you have virtual images. So you have to use this formula always with the sign convention for it to work for all cases. So you have to keep that in mind. And the other thing that I wanted to talk to you about, just to expand on whatever we've discussed so far, is this. When you apply the law of reflection, you take a point source or a point object, and take a point object, and then you have a mirror, any type of mirror. It can be a concave mirror, it can be a convex mirror, it can be a plane mirror, it can be any type of, or it can be other types of mirrors, in some exotic mirror. Okay. Whatever be the mirror, you take a point object and you draw rays from that point object and ensure that those rays obey the law of reflection, and then you can find whether or not they will form a real or a virtual image. Okay? And if you can do it for a point object, that's a basic unit. Then you can do it for a line or a linear object. You can do it for a linear object, then you can do it for an aerial object. If you can do it for an aerial object, then you can do it for a volume object. So the basic unit is a point. Any source you take, for example, you're seeing me, I am a light source now. So light travels in all directions from me, and some of the rays reach the camera, and that is what you are able to see right now. But I am a three-dimensional object, but then you can look at me as a collection of points. So from each point, lines go in different directions. Okay? So the basic unit is the point source. So let me draw that here. So you have this mirror, and let's say this is the axis of the mirror, and let's say I take a point. I can take the point here, I can take a point there, I can take a point anywhere, or even I can take a point on the line itself, doesn't matter. And let me take a point here, some random point here. Okay. So what this point source does is it's sending rays in all directions. Right? So energy, light energy, goes from here in all different directions. And they also come to us, and light cannot go the other side, on the other side, because you have blocked those rays. But you can see this, light is traveling in all different directions, and some of this light will travel, some of this ray, okay, these rays travel and hit the mirror. Okay. So this is a mirror. So these rays hit the mirror. You see, if the mirror is big, then a lot of rays will hit the mirror. The mirror is small, then only a certain number of, a less number of rays will hit that mirror. So the bigger the mirror, the larger or the more number of rays it collects here. So what happens is that after these rays hit this mirror, then they will obey the law of reflection, and then they will get reflected like that. So, image will be formed here. You see, if it's a smaller mirror, then less number of rays will meet here. So, the intensity of the image will be less. If it's a bigger mirror, then a lot of rays will meet here, and the intensity will be more. So, the bigger the mirror, the more intense this point will be. And if it can happen for one point, it can happen for any other point. Suppose if I have a line here. Okay, so now you see, now the line is a collection of points. So the same thing will happen for this point, or this point, or this point. I can draw these lines for all these different points, and all of them will form their images here. Okay, here, 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 here. So this point clearly will make an image here. You can imagine this today. So light travels from this point in all different directions, and it will hit here, then it will hit here. So the rays will converge and come back and then form the image there. So what happens for one point happens for all the other points on the line, and then the image is formed. I want you to understand this. Okay. The main thing is the law of reflection. Out of all these millions of rays that hit the mirror, I am going to take just two rays. That's what we have been doing. Maybe a ray which is parallel to this axis, and I'll say I'll take a ray which is parallel to this axis like that, okay. And maybe another ray that goes through the focal length or something, okay. Then you see this is going to be like this, right? Okay. So then this must be the focal length. Okay. So this is the focal length. It's going to be my F. So I have taken a ray parallel to the axis, it's going to this. And then I can take another ray that will go through this. Okay, and let's see, it kind of will come back and meet the same part. Okay, now I'll take those two lines, this line and this line, to find this point. So I'm using these two lines only to find that point. Okay, like this. Something like that. Okay. So I'm using these two lines to find this point. Doesn't mean that there are only two lines which meet at this point. All the other lines meet here. You should not forget this. This is a basic understanding that will help you do a lot of problems very easily. So this is what you need to understand. Okay. Now, in the 10th standard, you have come across this question: what happens if I blacken half of the mirror? Suppose I blacken this mirror, this part. Okay. Maybe the top part, or maybe something like this. I blacken this part. I can blacken any part. Okay. Either the top half or the bottom half, or something in the middle. I can blacken anything. Now, are you going to tell me that because you have found this point using these two rays, now these two rays are going to hit this, and they'll get absorbed. There will be no reflection. So, are you going to tell me that there will not be an image? Because the rays that you send are absorbed by the surface. No, they are not the only two rays. You are using those two rays to find this point. But they are not the only two rays which make the, form the image here. See, there are all the other lines, and this is not blackened, this is not blackened. All the other lines will get reflected. They'll obey the law of reflection, come and then make an image there. Okay? But what is the difference? You see, this point previously was very bright. Why? Because all the lines were converging here. They met here. But notice, the lines that fall on this blackened area, they won't get reflected. So those lights will not contribute to the brightness. So they will get absorbed here. They won't come here. But only the other lines, other rays will come and meet at this point. So you see, now you have less number of rays which meet at this point than before. So the intensity of this point will be less. Okay, the brightness will be less at this point now because I have blackened it. So keep in mind, you are using these two lines only to find this point. It doesn't mean that only those two rays are contributing. All the other rays, the millions of rays, they are contributing to that point. So if you don't have those two lines, doesn't mean that there will be no image. Okay? These two lines are for your convenience to identify the point. Keep that in mind. Okay. Now let's talk about a plane mirror, the mirror that you use every day. Yeah, the mirror is going to be something like this. This is a mirror. Again, I can take any object. I can take a line object or a point object or an aerial object or anything. I'm going to take a point object. That's a basic unit, right? So let's say I'm going to take, this is a point object here. Again, as we said, this is going to send light in all different directions. Because I will be able to see it, you will be able to see it, somebody else will be able to see it. It's going to happen. But you see, these lines we are not bothered about. So they're not hitting the mirror. We are studying the mirror, right? What is happening to the mirror. So now you see this is going to hit here. Okay, so these are the lines bothered about. Now, what will happen is this. Each ray will obey the law of reflection, correct? So for this surface, this will be the normal, and this will be the normal. I should try it like this. The normal, and this will be the normal here. This will be normal to the surface. You can see the normal drawn for this. So clearly, because this is sitting here, so this is the angle of incidence, then angle of reflection will be something like this, and this will be something like this, and this will be something like this. You can see that in the plane mirror, here there is convergence, here there is divergence. They go hit and then they go the other directions. They diverge from these points. Okay. So this is not going to form a real image. This will form a real image because there is convergence. You can capture it on a screen, but they are not meeting. These lines after reflection are not meeting anywhere. So then how will they even form an image? There is no real image that can be formed. So now what you need to do is you have to identify the point where they will form the virtual image, which cannot be captured on screen, right? So you look at this way. Looks like it is coming from a source somewhere here, right? I'm seeing this, so it looks like it's coming from a source somewhere here. Only this will reach me, right? So likewise, look at this way, then it is coming from a source, something like this. And look at this. Probably. not drawn it to scale, so I have to live with it. It's like that, okay? If drawn it, if the law of reflection is obeyed, then it will be. If I drawn these with scales and units, it will be perfect, but now I have to live with this. So let's say this is the image. So it looks like this ray is coming from there, and this ray is coming from there, and this ray is coming from there, and this ray is coming from there. So kind of. So this seems to be the object from where these lines come. Okay. So now clearly I'll say that this is a virtual image. So the light looks like the lines, the rays originate from this point. So you can see that this distance and this distance will be the same. I have not drawn the picture to scale, but you can, if you draw it to scale, then all these things will fall in place. So this distance and distance will be there. Then you have a virtual image here. So if this can happen for one point, then it can happen for a line. So that line will all be there. In this case, it won't be inverted. It will be erect and virtual. Okay. If we have a line here, let's say this is the center or something like that. So then I'll have something like this. Okay. So like that. Erect line, and it will have the same size, because if it is here, it will be there. Just like that. Draw it properly, then the point over here will form an image here. Same distance as the object. And the point over here will form an image here. Point over here, form an image here. Point over here, form a virtual image there. Okay? So then, this erect, virtual. So this is how the image will look like for a plane mirror. So does it mean that you can never get a real image out of a plane mirror? Will a plane mirror always produce a virtual image like this? Well, no. Okay, in some special cases, the plane mirror will form a real image. So what would that condition be? So look at this. So I have a concave mirror, it's converging these rays, and now if I put a plane mirror here in the path, then what is going to happen? What is going to happen is that the law of reflection will be obeyed. You see, I'll use a different color. Maybe. This line will get reflected there, just like that. So you see, now you get a real image out of the plane mirror. So if you take a plane mirror, and if lines, the rays come like this, then clearly, and again obey law of reflection, and you can get a real image. This can be captured on a screen. This cannot be captured on a screen. You can only see that it is on the other side of the mirror. This is a virtual image. And that is because the lines, the rays reach it like this. But if the rays reach the mirror like this, then it will form a real image. I want you to understand this. Okay? So there are basically two things. You are using these lines for your convenience, the green lines, the parallel line that goes through the focal point, and the line, the ray that goes through the focal point will be parallel to the axis. And all these things we are using for your convenience, but we need to remember that all these rays will obey the law of reflection. That's very important. Okay. And these lines help you identify the point at which the image will be formed. That's the only purpose. If you don't use these two lines, it doesn't mean that the image will not be formed. Okay? You have to understand that. And in a plane mirror too, the law of reflection will be obeyed all the time on any surface. Even if I take a mirror like this, you see it's not a very regular mirror. Okay? And if I have an object, you see you have a collection of mirrors there. But it doesn't matter. Any ray that is hitting it, any ray that is hitting the mirror, then you have to draw the normal for this surface. I don't know, maybe the normal for this is something like that. Now, this is the angle of incidence, and this will go like that. Okay? And maybe this will hit here, then the normal surface will come back, and maybe it will hit here, then it will come back, and maybe something like this. Then see the normal is going like that, and it's going to be reflected like this. You see, and this may get reflected off of this surface too. So all these things complicated things could happen, but all the rays that go from here, they have to obey the simple law of reflection. So this may result in you getting many images, real images. You can capture many real images after reflection on a sheet, and many images, many virtual images on the other side. So all these things can happen here. Okay, but the basic point is all the rays at each and every point on the mirror will obey the law of reflection. Okay, so maybe this will form an image here, and this will form an image somewhere, and this will form an image somewhere. So all these things can be captured on a screen. And if you take these things, they will form a virtual image here, virtual image here, virtual image here. Then this will be a combination of many real images and many virtual images for the same object. Okay? But this is a very simple case. One object, one image. But in all these cases, the law of reflection must be obeyed. I want you to understand this. We'll do a problem. And this problem is not given in your textbook. I've taken it from a different book. But I think this problem exemplifies some of the concepts that we've discussed so far. Okay? So I'll do the problem now. Let me read the problem first. A point light source lies on the principal axis of a concave spherical mirror with radius of curvature 160 centimeters. Its image appears to be back of the mirror at a distance of 70 centimeters from the mirror. Determine the location of the light source. Okay. So what is given? You have a concave spherical mirror, and there is a point source, and that is kept on the principal axis of that mirror. The radius of the mirror is given, and it is said that this object appears to form an image on the other side of the mirror, which means it is virtual, it's not a real image. If it is a real image, then it will form on this side, which you can capture on a screen. But this is happening on the other side. Okay, so you are getting a virtual image, which means that this object, the point source, must be kept between the pole and the focal length. Okay, so that is immediately that should strike you, because it is forming a virtual image. That will happen in a concave mirror if you keep the objects between the focal length and then the pole. If it is beyond the focal length, then it will form a real image on the same side. So that should strike immediately. Okay. So this is between the focal length and this. But you don't have to worry about it. But what I'm saying is, immediately it should strike you, but we'll confirm that later. Okay? But it's not critical. You can blindly apply the formula and get the results. But I want you to know that even before you put pen to paper, you know what the solution is going to be. So that is what. So you are forming a virtual image, meaning that you have kept the object between the focal length and then the pole of the mirror. Okay, let's see. And what is given? The radius of the mirror is given, which is 160 centimeters. If R is 160 centimeters, then the focal length must be 80. So even before I do anything, I know that the answer has to be less than 80, because I have kept it between the focal length and the pole, the object. So the focal length is 80 centimeters, then my ultimate answer, the answer that I arrive at, must be less than 80. So this I know before even I put pen to paper, or pen to the board in this case. Okay, so what is given? There is a mirror, concave spherical mirror, and then you have the principal axis of the mirror. Then I have the point source here, and then the point source seems to make an object here, image here on the other side. Okay, and that is, this is pole, and focal length is a mirror. I am not bothered with any of those things. This is pole, and this is the principal axis. Notice that you see, I can't use those laws, right? The rules I gave you. Line, a ray which is parallel to the principal axis will go through the focal point. Okay, you see, it is on the principal axis, so I can't even use that. Okay, but what do I know? Okay, these lines, then they will obey the law of reflection. Okay, so the normal would be somewhere here, and then it will go like that, and then finally it will diverge. This will diverge actually, won't converge, because as I told you, it's kept between the focal point and then the pole, so it will diverge now. So the virtual image will be formed there. But all this is not required for you. We'll go ahead with the formula now. Okay. Why I'm explaining this is because even before you do anything, you know a lot of information. You know how the solution is going to be. That's what I'm trying to drive at. Okay. So what's the formula now? What's the formula we're going to use? So 1 by f is equal to 1 by v plus 1 by u with the sign convention. If you're going to use this with the sign convention, you don't have to worry about where you have kept what. Okay? So you are going to use the sign convention. But what is given? Your radius is given. Radius of this sphere is given. That is 160 centimeters. So which means, what is the magnitude of f? F is going to be r by 2, right? Just r by 2. So f is going to be equal to 80. But now you see, this has to be the concave mirror. So we measure all the distances in this way. So that will be minus 80 centimeters. I mean, if you think about it, even r must be minus 160. So this is a pole, and the center will be somewhere there. So from the pole, you are going in the opposite direction to the direction of light. Light is in this direction, right? So we will be measuring in the opposite direction. So this itself will be minus 160. But let me not worry about that. But I know that f is equal to minus 80 centimeters. So 80. So on this direction it's minus 80. Okay. Next, the image is formed at a distance of 70 centimeters on the other side. Here, from the pole to this is 70 centimeters. So this is your V, right? This is your V. 70 centimeters. Okay, fine. So your V, okay, your F, you said is minus 80 centimeters. And then your V now is 70 centimeters, alright. But what is the sign? I told you, without the sign you cannot use this formula. What's the sign? Is it plus or minus? Well, this is the pole, and the image is found on this side. This is the direction of light. So I am measuring the distance in the same direction as the direction of light. So this will be 70. So that is 70 centimeters. Okay? I don't know you. Now I need to find you. Okay? So this is going to be 1 by minus 80 equals 1 by plus 70. This is plus 70 plus 1 by u. Okay, now what is 1 by u? 1 by u is equal to minus 1 by 80, and you bring it here, and minus 1 by 70. So this must be equal to minus of 1 by 80 plus 1 by 70, and that will be minus of 70 plus 80 by 80 into 70, right? Okay. So 1 by u is equal to minus 150 by 560. This and this will cancel. So this is going to be minus 15 by 56. Okay? So what is u? U is minus 56 by 15. It will be less than 4, right? Because like 4 15s are 60, so you got only 56 there. So it is, the answer will be less than 4. Okay, maybe 3.8 or something. I don't know, it's going to minus 3.7 or something. Okay, I don't know. So we can calculate it's approximately equal to this, is what I'm saying. Okay, so centimeters. You see, your u is now minus say 3.7 centimeters or something. Note this, when you apply this formula with sign convention, the value you get for u will also be with the sign convention. Okay, so now this negative sign tells you that u is on this side. Okay, suppose you get a positive number, say 3.7, and your answer is wrong. Why? Because you should always get it with the sign. So if the plus is a sign, then which means that the object is kept on the other side. So that cannot happen. If you keep the object on the other side, there is no reflection, or no law, no reflection obeyed. Nothing will happen here. So if I got it with the plus sign, then somewhere I made the mistake. That's what it is. So u minus is correct, because the answer you will get will also be with the sign convention. Okay, so u is minus 3.7. So use this formula always with the sign convention. Let's do example 9.3 from your textbook. An object is placed 10 centimeter in case 1 and 5 centimeter in case 2 in front of a spherical concave mirror of radius 5 centimeter, radius 15 centimeters. Find the position, nature and magnification of the image in each case. Okay, an object is placed 10 centimeter and 5 centimeter in front of a spherical concave mirror of radius 15 centimeters. Then find the position, nature and magnification of the image in each case. Okay, so this is example 9.3. Something similar to what we did just a while ago. So you have a spherical concave mirror. So So there is an object placed in front of it. Okay. Maybe here, there, it doesn't matter. Okay. So the distance is given 10 centimeters and then 10 centimeters and 5 centimeters. There are two cases. Okay. What else is given? The radius of this mirror is given. That's 15 centimeters. Okay, first. Then what is asked? Position and okay. U values are given, right? The U1, the first case, is 10 centimeters. And U2, the second case, that is 5 centimeters. There are two cases. First you keep it at 10 centimeters, and next you keep it at 5 centimeters. That's why I'm calling it as U1 and U2. But notice here, I can't just take these numbers straight away. I need to assign signs to them. Okay? First, R is 15 centimeters. So this is the pole. So the radius is going to be in this direction, right? It's going to be here. So I'm going to measure radius in this direction. So the object is going to be kept somewhere here. Let's say this is the object. It's the object. So light will travel in this direction, but my measurement is in that direction. So my radius is minus 15 centimeters. I'm using sign convention. So that gives me my F is equal to minus 15 by 2 or 7.5. Minus 7.5 centimeters. You see with the sign. I'm getting them with the sign. Second, the first case. It is kept 10 centimeters in front of the mirror. So the object is here, right? So from the pole, the measurement is like this, in the direction opposite the direction of light. So that's going to be minus 10 centimeters. In the second case, it's kept at 5 centimeters. Then that will be somewhere closer, right? So that would also be minus. I got U, I got F with the signs. Now what do they want? They want the position of the image. Position, nature and magnification. They want position, nature and magnification. First, how do I find the position? Where am I going to get my V? Whereas this is the object, where is going to be my image? That is the first thing, that is the position. What I'm going to use now? The mirror formula. 1 by F is equal to 1 by V plus 1 by U, or 1 by U plus 1 by U. How we know with sign conventions. So this is 1 by minus 7.15 by 2, right? So minus 15 by 2, that is equal to 1 by V. I have no idea. What is U? Plus 1 by, the first case, minus 10. Don't write 10, it's always minus 10. You write it with sign convention, minus 10. So this becomes, 2 will go up, 2 by minus 15 is equal to 1 by V minus 1 by 10. Okay. So what is 1 by V? 1 by V is going to be, if I bring it here, it's going to be 1 by 10 positive minus 2 by 15. So what would be my LCM? Okay, so this would be, let's say 150. It's going to be 15 minus 20. 2 into 10 minus 20. So this is going to give me minus 5 by 150. So 1 by 50 minus 1 by 3. Minus 1 by 3. Okay. So if 1 by V is minus 1 by 3, 1 by V is minus done it right? No. 150, 5, 3, 30, right? That's how it should be. I missed it. 0. Silly. Okay. So 30. So 1 by v is minus 1 by 30. So v must be minus 30 centimeters. So notice here that when you calculate v, you get it with the sign convention, meaning that v is on this side. Okay, v is on this side. So what is, that's understandable, right? So you have f here. F is how much? 7.5 centimeters, and clearly c will be 15. This is c, this is f, this is c. So from the pole it is 15 centimeters. Okay, and where we kept the object? The object you have kept is 10 centimeters. It's between f and c. So we kept it between f and c. So this is 10 centimeters from the pole. Okay, so if you keep the object between f and c, then the image will be formed back. So if you keep the object here, then the image will be formed between C and F. So this is where the image will be formed. If the object is here, the image will be formed here. But when you keep the object on C, the image will be formed at C. Okay? The object is at C, the image will also be at C. And if you bring it closer, then the image will move this way. So it is like this. You keep the object here, then the image is here. Then if you bring the object closer, then the image will move. And if you are keeping it at C, then the image will also be at C. But if you bring it closer to the mirror, then the image will move further and go like that. Okay? And at F, when you keep it at F, then the image will be formed at infinity. And if you bring it closer than that, and the image will be formed on the other side. Okay? So that is it. So v is equal to minus 30 centimeters. So the position in the first case 1, with u1. Okay? So I'll say case 1 is f is there, v1, u1. Should give you this. Okay? So position is this. What is the nature? Nature will be, what do they mean by that? Nature is like this. Is it an erect image or an inverted image? Is it an erect image or an inverted image? So, how is it? How do you do that? How do you calculate that? First, let me do the magnification. The third. I've done this. I will do this. Then I can find with the sign whether it is an inverted image or an erect image. Okay, so what have we got here? The magnification is equal to minus v by u. Again with sign. So this is minus of minus 30 divided by u1, right? So this is v1 this way. u1 is minus 10. So this is 30 by minus 10. It's going to be minus 3. So which means that this image is magnified, it is bigger than the original, the object. The image is 3 times bigger than the object. But then it is minus 3, so it is inverted. It is not erect. If it were erect, then I would have got a positive sign. So it's minus 3 means it's the image, the nature of the image is it is inverted. And it is also a real image. Why? Because it is forming on this side. I can capture it on screen. It is real and inverted. The magnification tells you that it is bigger than the object. So, nature is this. So when you talk about nature, it is real image on the same side. Real. I can capture it on the screen. It is inverted. Real and inverted. It is also bigger than this, than the object. So that is first part. So what about the second part? What will happen if I keep it at minus 5 centimeter? The same formula. So 1 by f is equal to 1 by, now this is going to be v2 plus 1 by u2. What is f? Again, minus 15 by 2. So 1 by minus 15 by 2, there is no change to that. And v, I have no idea. v2 I don't know. And plus, and 1 by u2 is minus 5. Always use a sign. Okay? And this will give me 2 by minus 15 equals 1 by v2 minus 1 by 5. So bring it here. So 1 by v2 is equal to 1 by 5 minus 2 by 15. So this will give me 15 would be my LCM. Then this is going to be 3 times, and this is going to be minus 2. So this will be 1 by 15. So my V2 is going to be just 15 centimeters. You see, I got that with the sign. What is the sign I got? Got positive. Positive sign is what I got, which means that it is in the same direction as the direction of light. So the direction of light is this way. That's how it reaches the mirror. It reaches the mirror like this. So the direction is like that. So for the pole, it is on this side 15 centimeters. Here. So this is where my image is. Okay. That's where my image is. So we got this. Okay, but that is understandable. You see, we are keeping it at 5 centimeters. Where is that? 5 centimeters is here, right? Because if this is 7.5, then 5 must be here. You are keeping it between the pole and the focus. So clearly, you are going to have an erect image. It's also going to be a virtual image. So the nature is virtual and erect. So what is the nature of this? Nature is virtual, because you can capture it on the screen, and erect. That is the nature. Okay. What is the magnification? So magnification would be m minus v by u with the sign. So minus, what's your v? Now it's v2, u2. So v is 15 plus 15. So divided by u2 is minus 5. So minus 15 by minus 5, I'm going to get 3. Okay, positive 3. So what does it mean? I'm getting a positive 3. So here also the image will be magnified 3 times. But we get a positive sign, meaning it is not inverted, it is actually erect. It's not on the other side. It's not inverted like that, it is erect. So you don't get that. Negative is not there. Okay? So this you can also visualize, you can see. But this is how you do this problem. Okay, the next problem we'll do is problem 9.4 from your textbook, exercise problem. It's a very important problem. I want you to pay attention to this. The way they have done this problem in the textbook is it's not exactly correct. It's an approximate approach. But what we are going to do here is a perfect approach. Okay, so your textbook is not exactly correct. So this is a very important problem. So pay attention to this. Example 9.4. Suppose while sitting in a parked car, you notice a jogger approaching towards you in the side view mirror of radius 2 meters. If the jogger is running at a speed of 5 meters per second, how fast the image of the jogger appears to move when the jogger is 39 meters, 29 meters and 19 meters away. So what is happening here? You are sitting inside a parked car and you are in the driver's seat and you are looking at the rear view, side view mirror. Okay? There is this jogger is coming towards you. The car is parked like that, the guy is coming towards you. And his speed is 5 meters per second. So that is how he is coming. Now you look at him in the mirror. In the mirror also he will be coming towards you, right? Because he is at some distance there. And then as he is approaching, then the mirror, it will look like that guy is coming towards you. The point here is, what would be the speed at which he will approach you? When he is at 39 meters, 19 meters, 29 meters, 19 meters from you. So 39 meters and 29 meters and 19 meters, his speed remains the same, 5 meters per second. But then the speed at which the image moves towards you in the mirror, that may not be the same. So they want you to find that. They want you to find how fast you are approaching, the image is approaching you when this guy is approaching you with 5 meters per second. And at different distances, the speed with which the image approaches you would be different. His speed doesn't change, but the speed with which the image approaches you as you look at it in the mirror, that changes. So how to do this? Okay. Well, let me take down this. Okay. Example 9.4. So you're sitting inside a car, and which mirror are you using in the car? Are you using a concave mirror or a convex mirror? It's a convex mirror. The mirrors that you use, the rear view mirror, the side view mirror, they're all convex mirrors. So the mirror is this. It's a convex mirror. It's not a concave mirror. So this is the axis mirror. So this guy is at some distance now, and this will form an image here. And as this guy approaches, and that image will also come closer. Okay, you're seeing it here, okay, in the mirror. Okay? So the image will appear to approach. So the speed with which he is moving is 5 meters per second. So right now he is at some distance. And then the speed with which this object, the image will be moving here towards you. The image will be moving towards you, and this guy will move towards you. Okay. I've drawn it already. Drawn this already. So this guy is moving towards you, and then the image moving. Suppose you are here, you are looking at in this mirror. So what is given? The radius of this mirror. The radius is given to be 2 meters, which means the focal length is 1 meter. Oh wait, what's the sign? Well, this is where the object is, this is where the pole is. Okay, where is my radius? It's on the other side. So how am I going to measure it? From here to there. Which direction? In the direction of light. So this will be positive 2, and the focal length of this convex mirror is also here. So from P to F, I am measuring it in the same direction, the direction of light, so that is also positive. So 1 meter, 2 meters. So I am not going to put negative into it. So I am good with the sign. Next, what do you want me to find? What is this Mustafa? What is his speed? You see, at any time, his distance is u. Right? u1, u2, u3, but distance is u. But that u is changing. The u is changing with the speed. So I will say his velocity, his speed, is actually, this guy's speed is actually du by dt. Because this is u. This is how it is changing. U is changing. So du by dt is 5 meter per second. So what do they want you to find? They want you to find the speed with which v is changing. They want you to find dv by dt. What speed your image is traveling towards you. So v is changing, right? With time. This way is approaching, image is approaching. This speed is given, du by dt. That's the speed at which u is changing. What is the speed at which your v is changing? Is it a constant speed? Is it something else? Is what you are going to figure out now. Okay. So where will you start? We'll start with this equation. The mirror formula. 1 by f is equal to 1 by u plus 1 by v. Okay. Irrespective of your u and v, your f is going to be constant. Your f is always constant. But now, how am I going to find dv by dt? Okay. So the way to do it is, I'm going to do a d by dt, the whole thing. If I do that, this is d1 by f by dt, d by dt 1 by u plus d by dt of 1 by v. Okay? F is a constant. Irrespective of what your u and what your v are, your f will always remain the same. So I'm going to differentiate f with respect to time. This will give me 0, right? Always 0. And I got 1 by u and d by dt. Okay, so I'm going to differentiate this function, okay, with respect to time. But what is this function? This is a function of u, right? Okay, I'll call this as a. Okay, it's like this. I'll call 1 by u as a function a of u, or I'll say, okay, a function, okay, I'll say function of u. I'll call 1 by v as a function of v. But notice that I'm going to differentiate a function of u with respect to time. So what would I do? When I differentiate a function d by dt of f of u is equal, so this is a function of u and this is a function of time, okay, but u also depends on time indirectly, right? So f, u depends on time, so f depends on time too. But what you got here is a function of u. So then how do you do this? This is equal to df by du into du by dt. Okay? So df by dt is actually df by du into du by dt. So du and du will cancel, then df by dt is what you will get. So this is what you know from your maths. Okay? So that's what we're going to use here. So what I'm going to do here, I'll differentiate this first with respect to u and then multiply the result with du by dt. So if I differentiate this with respect to this, so this is actually 1 by u, I'll get minus 1 by u squared, right? 1 by u with respect to, okay, what I'll do it here. Okay. So what is the function now? My function f of u is actually 1 by u. Then df by du will be equal to, and is also du power minus 1, so differentiating minus 1 times u to the power minus 2, right? So this will be minus u to the power minus 2, it will be minus 1 by u square. So that's what I got. So that is my df by du. This is my df by du. And I need to multiply that with du by dt. Okay? Again, let me come to this. So this is equal to, and if I do that, f of v is equal to 1 by v is equal to v to the power minus 1. So if I do df by dv, differentiating f with respect to v, then that is going to be equal to minus 1 times v to the power minus 2. So that will be minus 1 by v square. See, minus 1 by v square into now dv by dt. So this will give me d by dt. Okay. So d by dt of this is actually this. D by dt of this is actually this. Okay. This is 0. Okay. This is a constant. F is a constant. So it doesn't change. There is no change with respect to time. The focal length doesn't change. So it's 0. Then I bring one of them to the other side. Right. So I'll bring dv by dt. Okay. So dv by dt to 1 by v square equals minus 1 by u square into du by dt. So dv by dt is going to give me minus v square by u square into du by dt. So this is the expression I get. Okay. So what is du by dt? Du by dt is actually the speed with which this guy u is changing. Yeah. The speed with which u is changing is 5 meters per second. That's the speed with which that guy is coming to you. And dv by dt is the speed with which v is changing. That is the speed with which image is coming to you. But is it a constant? This is a constant. Du by dt is a constant. 5 meters per second. Wherever you are. But is this dv by dt a constant? No. Notice that this has v and u in its equation. Which means dv by dt is not a constant like du by dt, but it can change with respect to its v and u. Okay? So this is a constant, but this is not a constant. So even though this guy is moving at a constant speed, the image will be moving at you with varying speed. Okay? I want you to understand this. Okay. Now, the question is, what is the speed of the image when your u is 39 meters? The first piece. What's the speed? First, when u is 39 meters. Okay. When you say u is 39 meters, it's minus 39, right? Always. It's minus 39. Minus 39 meters. Okay. But u squared will become u squared 39 squared. So u squared is going to be simply 39 squared. Okay. Meter squared. But for that u, you need to find v. So how do you find v? Use this expression. Let's do the mirror formula. The mirror formula is 1 by f is equal to 1 by u plus 1 by v, and that gives you 1 by f is 1 meter, right? So 1 by 1 is equal to 1 by u is minus 39. Minus 39 plus 1 by v. So 1 by v is equal to, we bring it here, 1 plus 1 by 39. That gives you 40 by 39. That's your v. 1 by v. So v is equal to 39 by 40. So when u is minus 39 meters, v is 39 by 40, roughly 1 meter, okay, distance inside the mirror. Okay, so this is positive, this is negative. Keep that in mind. So you have found that. So if u is 39, v is 39 by 40. So you plug in those things here. So what is the dv by dt? Your dv by dt is equal to minus, what is v squared? V squared will give you 39 squared by 40 squared divided by u squared, 39 squared, and then multiply the whole thing multiplied by du by dt is 5 meter per second. 5 meter per second. You see, this and this will cancel, so you will get minus 5 by 40 square, 1600. So dv by dt is equal to minus 5 by 1600. So that will give you minus 1 by 320 meter per second. It will look like a very small speed. Okay. So why do you get the negative sign? Obviously, v is in this. The object is moving in this direction, so the image must be moving in this direction. So it is opposite to that. So you get a negative sign here. Minus opposite direction. Okay, minus means direction opposite to the direction of this one. Okay. So if I have taken this, because I have taken this to be positive, this direction positive. If I have taken this direction to be negative, then this will be positive. Then we move in this direction. So opposite direction, that is what it means. That is what the sign tells you. So I have done that for one position when u is at 39 meters. So you can do the same thing when u is 29 meters. When u is 29 meters, see, look at this. When u is 39 meters, v is 39 by 40. Okay, when u is 29, it will be 29 by 30. And when u is 19, it will be 19 by 20. So, accordingly the speed will change. So this is the exact way of doing this problem. What they have done in your book is slightly different. They have approached it approximately. Okay, they have used deltas. They have not used d's, du by dx. Okay, they have used the deltas. Okay, they have taken for some distance this is happening, sometimes happening. So that is not exact, but this is at every instant. This is the most accurate way of doing this problem. The way it is done in your textbook is not very accurate, because you get minus 1 by 280 for this in your textbook. Okay, instead of 320 you get 280. Yeah, close, but not really exact. But this is exact. So I want you to understand this. It's a very important problem. To understand this problem, you see, it combines quite a few things. Okay, it combines speed and velocity with the mirror formula to give you this value. Okay, so when you do problems like this, then you understand both the concepts better. Okay, hope this is clear to you.